In this video, we'll briefly discuss a convolutional variant of the restricted Boltzmann machine. So we saw how to take a normal feed-forward neural network and adapt it to images by making it convolutional. Now, what about designing convolutional neural networks that are unsupervised? So for instance, we've seen the restricted Boltzmann machine as a type of neural network, but that can be unsupervised. It can learn about the distribution of the data to be able to extract features without actually providing labels. So can we design a convolutional variant of the RBM? Well, yes, and one way of doing this really is just to apply these similar ideas we've discussed in the convolutional neural net in the feed-forward supervised case and adapt them for the unsupervised case. That is, have hidden units that are locally connected, that share parameters, and that are divided into feature maps, and introduce a notion of pooling units. So that's exactly what Unlak Lee and his colleagues in 2009 have done. And so I'm going to briefly describe what they've done. So what they do is that they again define an energy function in the RBM where you have hidden units that interact with some visible units in a visible layer, and they interact through some connections that are weighted. We also have some biases for the visible and hidden units. But now, and I won't go into details of this notation here, but now essentially a hidden unit in the feature map K at a position ij in that feature map is only going to be connected to a neighborhood. And in this notation here, the neighborhood is indexed by this R and S variable here. So where essentially we have R, which is right here, which is has a value from 1 to NW, and NW is essentially the size of the receptive field of the hidden units in the filter maps. If we write it into a more convolutional notation, then essentially all the filter maps, which, because it's an RBM now, a filter map actually corresponds to a filter map of binary random variables, is going to be connected, or it's going to be multiplied by the result of performing convolution of some weight filter with the original input V. V is actually, here it's in italic, but in the notation here they're using V for vectorial matrices, so it should really be in bold here. So we're taking that image, convolving it with some filter map parameter matrix, and we multiply the result of this element-wise with the stochastic binary hidden units in the kth filter map. And then we add those up, and these terms are now involved, now define the energy function in the convolutional RBM. So that takes care of introducing this idea of local connectivity and parameter sharing across hidden units, and segmenting the hidden units into feature maps. Now, what about pooling now? How do we introduce this idea into the RBM? So Lee et al. Introduced the notion of a probabilistic pooling type of unit, and the idea is as follows. So we have a unit, say here, which is in some feature map layer, and it's, as we see, locally connected within just a receptive field within the visible layer, and that unit will belong into a local neighborhood where there will be other hidden units within the filter map. And now we'll add another layer right on top of it, these pooling units P, and they will be equal to 1 if only if at least one of the hidden unit in its corresponding neighborhood in the filter map right below is equal to 1. So if there's at least one binary unit here which is equal to 1, the pooling unit will be equal to 1. So this is as if, and otherwise it's equal to 0. So really just the pooling unit is equal to the max of the hidden units in the filter maps, associated filter maps right below. And another thing that they propose is that within a pooling neighborhood, this neighborhood where we are taking the maximum over the binary hidden units, we also impose that there can be only one hidden unit which is equal to 1. And so this will introduce the kind of competition that we see in local contrast normalization in regular feed-forward convolutional network. So it means that within the neighborhood, there's actually only one feature that will be stochastically active in the generative model of the restricted Boltzmann machine. So in other words, if we write as with this notation here, the computation that corresponds to computing the pre-activation of the filter map, where here they're just assuming there's a single input channel, so we just have one convolution to do, and they also introduce some bias. So this I notation here, if we use it, the probability of a hidden unit being equal to 1 is going to be the exponential of the pre-activation divided by 1 plus the sum over all the other units in the neighborhood to which the hidden unit hkij belongs to of the exponential of their pre-activation. So this is just to take into account the fact that the other hidden units also have a probability of being equal to 1. And the 1 here is for the case where none of the hidden units in the neighborhood are equal to 1. They're all equal to 0, in which case, if we look at the energy function, we'd get a 0 term that's multiplying all the pre-activations of all the hidden units in the neighborhood. Okay, so we essentially have a sort of softmax over these hidden units in that neighborhood, but with an extra possibility, which is none of the units are equal to 1, and they're all equal to 0. So it's kind of this extended softmax kind of activation here. And then the pooling unit, well, it will be equal to 0 with probability 1 over 1 plus the normalization. So that's essentially the case where all, so if the pooling unit is 0, it means that also all the hidden units are equal to 0. So that's the extra term to make sure that all of these probabilities of each being equal to 1 and the case where they're all equal to 0 sums to, this whole thing sums to 1. So now when we're going to sample, when we say performing Gibbs sampling, where we're sampling the value of the hidden units H and the pooling units, what we have to do is for each neighborhood, we have to sample from that distribution here. So we determine whether which of the hidden unit is active or whether none of them are active. And we determine this using this sort of extended softmax kind of distribution. And then, if we sample and we're performing Gibbs sampling, and we sample all the value of the hidden units, then sampling the visible units if we're assuming the visible units are binary, and again, we could similarly extend to other types of visible units using the same ideas, we would just take the hidden layer feature maps and convolve them with their corresponding matrix of parameters, their filters, and summing over all the feature maps. And then that convolution at position ij plus some bias c passed through the sigmoid gives us the probability that this particular visible unit at position ij is equal to 1. And 1 minus that would be the probability of it being equal to 0. So essentially, the difference between a regular RBM is that when we're performing Gibbs sampling, instead of doing matrix multiplication, sigmoid sampling, matrix multiplication, sigmoid sampling, we're doing convolution, nonlinearity, which is this sort of extended softmax over the local neighborhood, sampling, and then convolution, sigmoid sampling, and then alternating like this to perform Gibbs sampling in this convolutional variant of the restricted Boltzmann machine. So using these conditionals, we can perform contrastive divergence because we have a way now of sampling these negative samples we need for updating the model. We will need the gradients of the energy function to derive our update for the parameters of the filter maps. And we can compute them similarly to how we compute the backpropagated gradients in a regular feed-forward neural network using convolutions. We can stack these RBMs one on top of the other. So we would actually use the pooled units as the values on which to train another convolutional RBM, and then we could get multiple layers of convolutional RBMs like these. And this, in fact, we can think of it as giving us a pre-training procedure that for a convolutional neural network that does not require just extracting patches. It would actually be trained globally on the images. And so so I've been going fairly quickly over this. To get more details about this, I encourage you to read Hunlak-Lee's and his colleagues' papers, which was published in 2009, and it's available on the website for this course.